Welcome back to Introduction to Microeconomics. I'm Keith Akucha. In this video, we're taking a look at social interactions in game theory. Specifically, we are going to be taking a look at simultaneous games and the Pareto Criterion. The idea here is really, everyday situations, like whether choosing, hey, do I drive or carpool to school? Do I contribute or not contribute to a group project? Do I put in that effort to reduce my carbon footprint? All of these involve strategic choices which are being made at the same time as other individuals. That is ultimately your payoff is a result of not just your choice, but also the choices made by others, and these other choices being made simultaneously, meaning you have to choose without knowing what they are choosing. There's going to be cases where we are better off acting strictly in our own interest. There's other cases that we're better off cooperating. Sometimes that may be where we just by default end up. Sometimes we end up in conflict with that. The whole point of this video is to take a look at these scenarios, identify how we personally respond to this, and then be able to identify the likely outcome and if it differs in any way from one that may be the socially maximizing outcome. And we'll talk about those distinctions and differences as we go through. So ultimately, what are our objectives of this video? We'll take a look at these simultaneous games. We'll figure out how to play them, how to figure out the outcomes. We're going to then go, and as we do that, we'll define what we mean by Nash equilibrium and how to identify it. And we'll take a look at this whole idea of the Pareto Criterion and get that definition sorted out as well. So let's go jump over and get started. We'll start off with a classical case of game theory, something known as the prisoner's dilemma. So let's go jump over and have a look. So here we have a payoff matrix that is showing two different players. In this case, our two different players are Thelma and Louise. Now, these are two suspected criminals, and they've been picked up on a suspicion of a serious crime that is believed they have committed. Of course, the police don't actually have enough evidence to put them away for this crime, thus they separate them into two different interrogation rooms, question them, and then they offer each of them this same deal. If both of them, end up denying that, hey, they had anything to do with this serious crime, well, they're each going to get a 1-year jail sentence for the lesser outstanding warrants that they were both able to get picked up on. So it's kind of saying, hey, Thelma, hey, Louise, no matter what, you're going to jail for 1 year. But look, here's the deal. If you snitch on your partner, we will give you amnesty. We will forgive you for your outstanding warrants. And because you cooperated, we will let you go free. So, for example, Thelma, if you snitch, you get 0 years in jail, and Louise will go away for 10 years, dealing with that entirety of the sentence. Of course, Louise is offered that same deal altogether. Louise can similarly snitch on Thelma, have their entire past history forgiven, and get to go free, and Thelma gets to go to jail for 10 years. The problem is, of course, if they snitch on each other, sorry, we now have pretty good evidence that you were both involved in it. We can forgive you for your past crime that was a 1-year jail sentence, but if you were involved with this more serious crime, sorry, you're going away. The question is, what do you do? You're in this situation. You're Thelma or you're Louise. Do you stay silent? Do you deny? Is it the whole snitches get stitches? So just, hey, stay quiet, deny, deny, deny. We'll do our 1 year in jail and then we're free? Or do you go and say, hey, if I snitch on my partner, they go to jail for 10 years. That's a long time that I can get out of town, go and reinvent myself, recreate it all, and avoid the future consequences of this such that I'm safe. What do? Do you stay thick as thieves and deny? Or do you take advantage of this situation, snitch, let your partner go to jail, and you run free? Well, let's go through and figure out how we would want to work through this game to figure out what we would call the Nash equilibrium, which is the stable equilibrium in this case here. And the way that we play any of these games is by determining what we would call our best response. So what is our best response? Okay. And the way that we figure out our best response is we just say, okay, well, if we're Thelma, we don't know what Louise is going to do. Louise may deny, Louise may snitch. So we need to ask, well, let's just presume that we're pretty sure Louise is going to be a solid individual, will completely deny anything to do with this situation. Well, if that's the case, what is my best response to that? Well, my best response would be, well, I could either deny and get 1 year in jail, or I could snitch and get 0 years in jail. I don't know about you, but personally, 0 years in jail sounds better than 1 year in jail. So, Thelma's best response to Louise denying is to snitch. So we say, there we go, best response to deny is snitch. Similarly, we then go, well, okay, but what if Louise does snitch? What if Louise doesn't deny? What do we do then? Well, if Louise snitches, we could deny and go to jail for 10 years, or we could also snitch and go to jail for 5. What's better, 10 years of jail or 5 years of jail? I mean, they both suck, but which one's better? I think probably 5 years of jail is better than 10. So what we see in this situation is it actually works out that Thelma's best response is to always snitch, irrespective of what Louise does. If Louise denies, our best response is to snitch, and if Louise snitches, our best response is snitch. What we would say in this case is we would say that Thelma has a dominant strategy. That is, Thelma's strategy is to always snitch. She is always best off snitching, irrespective of what Louise does. So, again, Thelma has a dominant strategy to snitch in this case here. Now what we want to do, we've now played the game as Thelma. We know that Thelma's dominant strategy is snitch. We now turn the tables. As we turn the tables, we now want to play as Louise. And sorry, I took something for granted in reading these tables. First thing to realize as we read these tables is the first set of payoffs is always the row player. Now, I chose to start as the row player just because that's by default what I usually do, but that's just personal preference. I could have started with Louise just as easily. So first set of payoffs are always the row player's payoffs. The second set of payoffs, 1, 10, 0, 5, that second set of payoffs are always the column player. So in that case, Louise's payoffs. So let's turn the tables, let's play as Louise and see what Louise's best response is to each of Thelma's choices. Okay, so we are now Louise. In this case here, we want to say, okay, as Louise, what is our best response if Thelma denies? I mean, we've already gone through this. We know Thelma will never deny. Thelma's always best to snitch. But let's go through the full process just the same. Okay, so if Thelma's denying, we can either deny and get a payoff of 1, or we can snitch and get a payoff of 0. Again, that's 1 year in jail or 0 years in jail. Between those two, 0 years in jail sounds like the better deal to me. So in this case here, if Thelma denies, Louise's best response to deny is to snitch. Similarly, we do the same thing. Well, what if Thelma snitches? What is Louise's best response to Thelma's choice to snitch? Well, could either go to jail for 10 years or go to jail for 5 years. Which one is more ideal? Preferably 5 years in jail is better than 10 years in jail. So again, Louise's best response to snitch is to also snitch. What we see here is altogether overlapping best responses. Anytime we have overlapping best responses, well, that's not the right tool. Anytime we have overlapping best responses, we would say that this here is a nash, N-A-S-H, equilibrium. And I'll just abbreviate that to NE for our Nash equilibrium. This is where we would expect to end up in most cases if we were rationally playing this game and trying to get our best payoffs as possible. In this case, our best payoff is minimizing our time in jail. And what we see is that this Nash equilibrium is 5 years in jail, 5 years in jail, for a total of 10 years in jail. And this is just each player responding to what is best for them independently, individually. Question is this really the best outcome for them? In this outcome, just again, them all just individually responding to their own best incentives, they each end up in jail for 5 years snitching on each other. If they could just entirely sit here and look at this and plan it out ahead of time and know exactly what the other one's going to do, what's the best outcome? What outcome would they like to arrive at? Well, the outcome that they would jointly like to arrive at, that is the social optimal. The social optimal would be this one here, such that they have the least amount of jail time, only 1 year in jail each. So this is the interesting dilemma, the interesting outcome of the prisoner's dilemma, is that by acting in their own self-interest, we actually end up at a suboptimal outcome versus if we acted in the best interest of the other person. However, we are typically on that selfish side of things, and as a result, by acting in our own personal best interest, there are times just like this where we can end up actually in suboptimal outcomes. Okay, so a few definitions that we've gone through in working through this. The first, best response. What is your best payoff given the other person's choice? Thelma chooses deny. What is my best response to you choosing deny? Do I deny? Do I snitch? Snitch is the better payoff. Snitch is my best response. Where we have overlapping best responses, we get a Nash equilibrium. Now, any game matrix, any game altogether that we end up playing may have 1, may have 0, or may have many Nash equilibrium. That is, a game does not need to have one, and if it does have one, it does not need to be unique. One of the other terms we introduced here was dominant strategy. A dominant strategy is a situation where, given your best responses, you only ever pick one thing. In this case, Thelma had a dominant strategy to always snitch. Louise similarly had a dominant strategy to always snitch. So as they both have dominant strategies, when we have overlapping dominant strategies, we would also call this a dominant equilibrium. So in this case here, we have 2 equilibriums taking place. We have the dominant equilibrium because we have overlapping dominant strategies, and we have the Nash equilibrium, that is where we just have overlapping best responses. So a few different definitions laid out there. One of the other things we can do with this payoff matrix and the way that we played the game and figured out, hey, what was our equilibrium, our most likely outcome, is to take a look at all of these payoffs all together to kind of rate, hey, which payoffs are more preferred, which ones are less preferred. And that's one way that we can easily visually compare a social optimal versus where we end up as an optimal. And I guess I should back up for a second here. And yes, we've said, hey, this is the Nash equilibrium, this is the dominant equilibrium. I mean, the dominant equilibrium just tells us it's overlapping dominant strategies. Let's focus on the fact that this is the Nash equilibrium. Why would we expect ourselves to be here? Why wouldn't we, if this is where we end up, why wouldn't we ever leave? Well, the Nash equilibrium is what we would call a stable equilibrium. And that is even though we're better off here. we're much happier there. We are worse off there. No player can deviate from this without being worse off. That is, again, unless they collude, unless they work together, but that's outside the bounds of this game. In this game, they were put in their individual cells. They're acting individually, independently. No one player can change their strategy and be better off. Let's take a look. Let's say Thelma goes, oh no, we wound up here. Maybe instead of snitching, I'm going to deny. Well, if Thelma switches from snitching to denying, Thelma switches from going to jail from 5 years to 10 years. So Thelma's worse off moving away from that Nash equilibrium. Similarly, what about Louise? Well, Louise could go to jail for 5 years if she snitches, or it could go, hey, instead I will deny. Well, again, that'd be 5 to 10. Again, worse off to deviate from this Nash equilibrium, this stable equilibrium. So what we find is that this is the place that we are driven towards, given our own individual self-interest. And once here, there's no way to individually, there's no way to independently leave this without being worse off. Okay, let's visually, graphically view what this payoff matrix looks like in payoff space. And what I mean by that, let's just create a bit of a graph. So in creating a bit of a graph, let's go, here's our x-axis, sorry, there's our y-axis. Wow, there's our x-axis. Keep in mind, the way that we typically write payoffs is x, comma, y. That looks like a T. Let's try that again. X, comma, y. There we go. That's a little bit better. So, hey, if we're doing x, comma, y, and first set of payoffs are Thelma's, second set of payoffs are Louise's, well, then what we have is we have the horizontal representing Thelma's payoffs, and we have the vertical. My goodness, I'm having a hard time. We have the horizontal representing Thelma. We have the vertical representing Louise. And what we see for payoffs, years in jail, maximum is 10, minimum 0. So let's go, there we go, 0, all the way up to 10, all the way up to 10, and then roughly try to get about in the middle. There we have 5. There we have 5. If we were to then to plot these 4 points on here, what do we get? Well, we get something, I don't know, around there. That would be our first point. That is when we deny. Our next point then is going to be Thelma with 10 years, Louise with 0. So Thelma 10, Louise 0. There we go. That is deny snitch. And then the other extreme, 0, 10. So Thelma's in jail for 0 years. Louise for 10. And here we have snitch, deny. And then finally, we have our Nash equilibrium such that they are both in jail for 5 years. And in this case here, that is our snitch outcome. Okay, so here we can see all of those different payoffs all together and see where they fall. Then we could go through and say, well, hey, what is going to be each of their, where do they want to be? And ultimately, like we've already said, hey, this outcome here is far less time in jail. That outcome is altogether preferred. In fact, if we could move from snitch to deny, we would altogether, everybody would be better off. Thelma would have 4 years fewer in jail. Louise would also have 4 years fewer in jail. They would both have an improvement moving from snitch to deny if they could both work that out. So this deny outcome is really where we'd want to be. This is the social optimal. What we will see, this is the Pareto efficient point, and that is because we can both win, we can both be improving our outcomes from moving from our Nash equilibrium. I know I'm kind of dropping a few kind of terms. These are a little foreshadowing almost into what we're going to be taking a look at. Pareto criterion, Pareto efficient, Pareto improvement. I don't want to get to these just yet because the way these payoffs are backwards versus most of the cases we'll look at. And so in order just to maintain consistency, I'm just going to drop those nuggets right now. But we'll wait till the next example before we actually look at and define these, just in order to maintain consistency and make it clear. And the reason being, in this scenario, our payoff is a negative, years in jail. So we want to minimize our years in jail. Often, not always, but often what we are looking at are payoffs that are positives. How much utility do I get? How much profit do I get? How much monetary reward do I get benefit from one action over another? In all of those cases, those are positives, things that you would want to maximize. So a very different situation in terms of practice, but same thing in theory. You want to do the best off you can. Right now, what I really wanted to get out of this is just the ability to be able to turn these 4 payoffs into 4 points on a graph and be able to look at where they fall. Let's go carry on. Let's go take a look at another example, another game, and see how we would play and work through that one. Okay, so in this scenario, we have Cosmo and Wanda. Both of them have their options as to how to commute to work or commute to school, whatever it might be. That is, they can either take some form of alternate transportation, maybe that's bike, bus, electric scooter, I don't know, some alternative form of transportation, or they could choose to drive. Now, of course, if they choose to drive, that adds congestion to the road. They get the benefit if they're the only one driving, but if everybody starts driving, they get in each other's way, and thus their benefit they receive decreases because they're just stuck in traffic. I mean, keep in mind, you're not stuck in traffic, you are the traffic. Of course, the alternative side is yes, you get a benefit, but let's be honest, sometimes you're out in the cold, you're out in the rain, you're stuck waiting for a bus that doesn't come. So often you had to have that preference to drive over the alternative transportation option. So taking a look at that, what does Cosmos do? What does Wanda do given these two options before them? Now, again, it's a simultaneous game. Cosmo decides what he's going to do, not knowing what Wanda's going to do. And Wanda similarly is going to decide what to do, not knowing what Cosmos does. So let's go through, let's play this game. Again, I'm going to start with the row player, so I'm going to start with Cosmo for no reason other than just that's my practice. So what do we do here? So as Cosmo, we go and we say, what is our best response to Wanda choosing alternative transportation? If Wanda chooses alternative transportation, we either get a payoff of 4 or we get a payoff of 5. In this case here, this payoff is not years in jail. It's the amount of benefit we get. And I don't know about you, but I'd want more benefit than less benefit. So does Cosmo. Thus, in this case here, Cosmo would choose to drive. We then carry on and say, okay, well, we know what Cosmo would do if Wanda goes alternative, but what does Cosmo do if Wanda decides to drive? If Wanda drives, what is Cosmo's best response? Well, Cosmo could get a payoff of 2, or could get a payoff of 3. Again, in this case here, the better one is a payoff of 3. So in this case here, Cosmo has the dominant strategy. He will always choose to drive, irrespective of what Wanda's choice is. Okay, now playing as Wanda, we'll say Wanda's green in this case. We do the same thing. We say, what if Cosmos chooses alternative transportation? What is Wanda's best response to that choice? Well, Wanda could choose alternative herself for a payoff of 4, or could choose to drive for a payoff of 5. What we're seeing, just like in the last game, this is a symmetric game. That is, we are getting symmetric payoffs from both players. And so for 5, 5 is a better payoff. and Wanda chooses to drive. Alternatively, if Cosmo chooses to drive, what is Wanda's best response? Well, Wanda could choose alternative for a payoff of 2, or could choose to drive for a payoff of 3. Again, 3 is better than 2, so Wanda chooses to drive. Again, what we see is Wanda has a dominant strategy. In this case here, that dominant strategy is to drive. The result is we get both a Nash equilibrium as well as a dominant equilibrium, such that dominant equilibrium overlapping dominant strategies, Nash equilibrium overlapping best responses, and that takes place right there, Nash equilibrium at drive, drive. What we see, though, is that the total social benefit in this scenario of 3, 3, or a total benefit of 6, that's just the 3 plus the 3, is in fact the lowest out of all the possible social benefits we could receive. If Wanda does alternative and Cosmos drives 5 and 2, we would get 7, 7, and 8. Meaning from society's viewpoint, this gives us the highest social payoff. However, by each person acting in their own best interest, we end up at a suboptimal level. And in fact, more so, we end up at a level that gives us the lowest possible payoff of all the options available to us. And again, despite this, this is a stable outcome. We have no incentive to move by acting independently, by acting on our own. And again, just to see that, let's take a look at Wanda. If Wanda says, wow, this is suboptimal, maybe I should do something to improve and move to alternative. Well, if Wanda moves to alternative, Wanda's payoff goes from 3 to 2. So Wanda's worse off if she makes that decision. Similarly, what if Cosmo makes that decision? Well, if Cosmo makes that decision, says, yeah, okay, I'm driving, I'm going to switch to alternative, again, moves from a payoff of 3 to a payoff of 2, being worse off. The only way that we can altogether improve not only our individual, but societal outcome is if we could coordinate between ourselves and both move to this alternative option. However, here's the problem. Even if we were able to coordinate, even if we were both able to agree that we are better off here and move to this outcome, each individual has an incentive to break this. If we find ourselves here, well, Cosmo could go, cool, we've agreed to alternative. I could decide to break this agreement, switch to drive, and I would be better off. Similarly, Wanda could say, yeah, great, we've agreed to this. I'm getting my payoff of 4, but I could break this and just choose to drive, and I could be better off. Now, of course, both of those actors acting in their own best interest, breaking this agreement, and where do we wind up? Back at the drive outcome, which is the socially suboptimal outcome. And thus we are worse off again. How does this look like in terms of payoff? And then by taking a look at that, we can introduce that other concept I was talking about, the Pareto Criterion. Let's go build that payoff graph. So we're going to have our vertical, we're going to have our horizontal axes. And again, in this case here, our payoffs are always in terms of x, comma, y. So that is Cosmo, comma, Wanda. So our horizontal axis is Cosmo. Our vertical axis is Wanda. What do we have for scale? We have a maximum payoff of 5 and going down to 3. So let's just go 0. We'll put that as 5. We'll put that as 5. And let's just kind of ballpark where these different payoffs are. So, okay, alternative is 4, 4. So that's going to be something like this. Alternative. We then have 5, comma 2. That is Cosmo, comma Wanda. So 5 comma 2 is something like that. That is drive comma alternative. We have the other extreme, 2 comma 5. So that's 2 for Cosmo, 5 for Wanda. Something up there, and that's alternative comma drive. And then finally, we have our Nash equilibrium at 3 comma 3. That's going to be somewhere, again, just kind of ballparking this. I'm going to say somewhere around there, drive comma drive. Okay, so we have our 4 different payoffs being presented there all together. What we can then do, and like I said, we could have done this in our previous case with the prisoner's dilemma. It would just be a little bit funny because everything was reversed from the way we normally think of it in terms of payoff. But if we start at any scenario, let's start just at our Nash equilibrium. Let's just maybe highlight that. There we go. That's our Nash equilibrium, drive, drive. That's where we're going to end up because that's where it's stable. Any other point will eventually make its way to that, just out of acting in our own best interest. What we can see is that in respect to drive, comma, drive, anything north of here is a situation where Wanda is better off. Similarly, anything east of here is a situation where Cosmo is better off. Ultimately, anything that is up to the right of drive, comma, drive is a situation where both of our players are better off. That is, moving from drive, comma, drive to alternative, comma, alternative is a situation where they're both better off. Both players win, no players lose. Okay, let's keep that in mind. If we take a look at alternative, alternative, we see that nothing is up to the right of that. So nothing up to the right of that. There's no improvements that are possible to us from A comma A. A comma D, up to the north. Again, we see that there is nothing up there. There is no possible improvement from A comma D. Finally, take a look at D comma A, and again, nothing to the north, nothing to the east. So there is nothing up to the right of drive, comma, alternative. That is a improvement for us. The only one that exists is up to the right of our Nash equilibrium, up to our right of drive, comma, drive, which would be that move there from drive, comma, drive up to alternative, alternative, such that everybody wins, everybody is better off, nobody is worse off if we move to that scenario. Okay, what we've just seen here is we've been able to identify where improvements are possible. We have said, hey, A comma D, there's no improvement possible. A comma A, no improvement possible. D comma A, no improvement possible. D comma D, yeah, there is an improvement possible. We could both be better off moving from D comma D up to A comma A. What we are getting at in looking at it in this way is what we would call the Pareto Criterion. The Pareto criterion, as seen here, states that a given outcome is an improvement to another if at least one party would be strictly better off with no party being worse off. And that is the big part, is can we have a situation such that at least one person wins and no one loses? That no one loses is the big part there. In this case here, yes, moving from drive, comma, drive to alternative, comma, alternative, we get better for Wanda. We get better for Cosmo. So both are better off. No one is worse off altogether. So we would say that drive, comma, drive to alternative, comma, alternative is a Pareto improvement. a Pareto improvement occurs whenever at least one party is better off with no party being worse off. So in this case here, this movement would be a Pareto improvement. That is, if this is a Pareto improvement, we would say that AA Pareto dominates DD. That is, because this is a Pareto improvement, we are better off. This Pareto dominates that. Anything up to the right is going to be Pareto dominating something down to the left. The next definition we would want to take a look at is this idea of Pareto efficiency. And really, this is a pretty simple definition. There's not a lot of robustness to this. Just simply, it is a point is Pareto efficient if there's no Pareto improvements possible. And so taking a look at this, we could go and say, well, hey, A comma D, that point there would be Pareto efficient because there's no improvement possible from it. A comma A would be Pareto efficient because there's no Pareto improvement possible from it. And finally, D comma A, again, would be Pareto efficient because there's no Pareto improvements possible from it. Of course, the interesting outcome of this is that our Nash equilibrium, where we would end up just by playing in our own best interests, this is not a Pareto efficient point. It is not Pareto efficient because we could have a Pareto improvement going from drive to alternative, such that at least one party is better off with no one being worse off. In this case here, both parties are actually better off. So because the Pareto improvement is possible, this guy is not Pareto efficient. We would only have 3 Pareto efficient points, none of which being our Nash equilibrium. Okay, we've just thrown there's 2 other definitions up there, the one being a Pareto improvement. I've already walked and talked through this, we just didn't have it in writing. That is, the Pareto improvement is when a new outcome makes at least one party better off with no one being worse off. So again, moving from drive to alternative is a Pareto improvement. But then I've thrown on this other one, a potential Pareto improvement. Well, this is just more of a point of interest. This isn't anything to do with Pareto efficiency, right? Pareto efficient is just if no Pareto improvements are possible. Doesn't say anything about a potential Pareto improvement. What we mean by a potential Pareto improvement is when, yes, one party wins and the other loses. But the winner wins by so much that they could compensate the loser such that the loser is actually no worse off after this redistribution. And let's take a look at an example of this. So an example of this would be, let's start off taking a look at alternative, drive. So in this case here, Cosmos is engaging in alternative transportation, Wanda is driving. While this to alternative is not a Pareto improvement, because moving here, Wanda is worse off and Cosmo is better off. And we can see that, right? We can see that in the fact that A comma D, so that is A comma D, right there, we are at 2 comma 5. So moving to A comma A, Cosmo goes from 2 to 4, so gets +2. However, Wanda goes from 5 down to 4, so goes -1. What we see is this is not a Pareto improvement because although one party is better off, the other is worse off. But what we could see is that we could actually compensate Wanda for her loss such that Wanda would be no worse off and Cosmo would still be better off. That is, we have Cosmo getting +2. You have Wanda going -1, we have the potential for Cosmo to redistribute that 1 so that he's just left with +1. Wanda then is just left off with 0, so Wanda's no worse off. And on whole, that social welfare has improved. The size of the pie has still gotten bigger. One of the problems with potential Pareto improvements is there just needs to be the potential for this redistribution to take place. Whether or not this redistribution taking place does or does not happen is not part of the definition. It's just saying, hey, does Cosmos win by enough such that he could compensate Wanda for her loss, such that a party wins and no party is worse off? Doesn't say we have to, it just says, could it happen? That is, the other way to think about it is just a potential Pareto improvement is a bigger pie, such that, yeah, maybe some people's slices are growing, others are shrinking. A Pareto improvement is a bigger pie, such that everybody's slice has gotten bigger. So both cases are saying, hey, could we get a bigger pie? A Pareto improvement is, can we get a bigger pie with everybody getting at least the same size or bigger? A potential Pareto improvement just says, hey, no. Is the pie increasing such that everybody could have at least the same size? They don't have to, but just could they? Is that a possibility? So big distinction there between the two. Now, again, this is just more of an academic, more of a thought exercise. The whole idea of Pareto efficiency is entirely bounded around a Pareto improvement, not the potential Pareto improvement. That's just that thought. That's just that idea. Okay, the last element that I want to bring into this is we could also just use this payoff, not the payoff matrix on the left, but rather the payoff dot plot. Or I guess that's not a dot plot. That's more just a scatter plot. That's the word I was looking for. Thank you. That payoff scatter plot on the right, we could use this to evaluate our indifference curves, our levels of utility that we receive at each payoff. And that is, well, yeah, we might be getting payoff at one versus payoff at another. Ultimately, as individuals, we want to maximize our utility, not necessarily just our payoff. And we may have a situation where you actually get utility from other people getting satisfaction as well. That is to say, you may to a degree be altruistic. Altruism, or being altruistic, is getting that joy, getting that benefit by seeing somebody else getting benefit. This really is why we give to charity. This is why we help other people, is because we do have a degree of altruism to us where we gain, we benefit by seeing society, by seeing our community, our group as a whole benefiting. How far does our altruism go? Does it go just amongst our family? Does it go amongst family and friends? Or does it extend into the larger community on whole? This, of course, is a big area of sociology and the research that goes into sociology and psychology as to the differing levels of altruism amongst different peoples and different groups of people. But we do know that to a degree, there is a sense of altruism that takes place. So what we can do is we can model that and we can say, well, what are potential outcomes through a purely selfish view of this? And then what are potential outcomes through an altruistic view of this? So let me just clean up this scatter plot, and then let's take a look at it with some indifference curves and figure out what is our preferred outcome from an altruistic sense, what is our preferred outcome through a completely selfish sense. So give me a second, movie magic, and then we'll carry on. Okay, so here we have that cleaned up scatter plot. Again, I still have our Nash equilibrium of drive highlighted for us. If we had purely selfish indifference curves, so taking a look at our X player, that is Cosmo, if Cosmo was entirely selfish, Cosmo's utility is defined only by Cosmo's benefit. So in that case there, whatever benefit Wanda gets has no impact on Cosmo's well-being, on Cosmo's utility. The result of that, Cosmo only has preferences for Cosmo, and so the indifference curves would look just like a series of vertical lines passing through each point. There we go. And of course, just like in every other case, as you move away from the origin, you are getting higher and higher and higher levels of utility, such that altogether Cosmos' highest utility would be at drive, comma, alternative. And I mean, this kind of makes sense if we think about the context we're talking about, such that Cosmos gets to drive, that is, gets the convenience of driving, having the heated car, having the quick commute, and all the rest. And if Wanda is using alternative transportation, Wanda, or by default, everybody else, isn't adding to the congestion of the road, meaning Cosmos gets the convenience of driving, and everybody else isn't getting in their way, slowing it down, creating a traffic jam. So, just from that perspective, yeah, that entirely makes sense. Cosmos is best off when he decides to drive, and everybody else uses alternative transportation choices. Great, makes sense. The next runner-up, of course, is alternative, and that's simply just because Cosmos just concerned about Cosmos's benefits, doesn't care about Wanda, and so that's Cosmos's next best payoff. Finally, where we end up is the Nash equilibrium, not the worst, but not the best by far either, which is our drive-drive situation. And that's because, like we said, we're always going to have, if we are acting in our own best interest, we are always going to want to drive over alternative given the other's choice. Our best response is always drive. Okay, so we see where Cosmos wants to be given these payoffs, given Cosmos's utility and being entirely selfish. But what if Cosmos wasn't entirely selfish? What if, to a degree, Cosmos got some utility, some benefit from Wanda being better off? Well, if that was the case, again, it doesn't need to be drastic. It could just be just knowing that other people are better off gives you some level of joy. Well, we would get a little bit different. We could get an indifference curve mapping that looks something like this instead. In this case, again, we're looking at the indifference curves for Cosmos. And in this case here, we still have relatively steep indifference curves. We're saying, yes, Cosmo is altruistic. He gets benefit knowing that Wanda is benefiting, but generally speaking, he still primarily cares about himself. But what we see is, as Cosmo gets more and more and more benefit such that Wanda's is being driven to zero, well, that isn't great for him. He has that altruistic preference, hence why it starts to level out near the bottom of Wanda's benefits. However, as Wanda becomes better and better and better off, the indifference curves become steeper. Cosmo says, well, no, you're well enough off. I care more about myself now. Okay, so that's the idea to the shape of these indifference curves. Again, same idea. The farther we go away from the origin, the higher our levels of utility. The closer we get to the origin, the lower our levels of utility. What we see in this case is we get a very different indifference curve mapping, such as which indifference curve is actually making us the best off, which one we would actually prefer if we could get there. In the first scenario, if you were entirely selfish, your best outcome was that you get to drive and everybody else uses the bus or bike. That way there, you get to drive, you get the fast convenience of your vehicle, and the roads are empty. So you just get to whip where you're going quickly. If you are more altruistic, that is, you have these altruistic preferences, you don't care just about your payoffs, you also care about the other people's payoffs to a degree as well. Well, this changes things such that now the highest indifference curve is alternative. Yes, you still get the benefit from driving. You're still like, yeah, this is better than the drive because everybody's losing, everybody's stuck in traffic. But you recognize that all of those benefits from the other people, you take that as benefit to yourself as well. And thus, to a degree, you're willing, because you're altruistic, you're willing to contribute to the solution that is not being part of the traffic. And thus, you get alternative as the highest pay off the highest indifference curve in that sense there. All of this to say, our Nash equilibrium, where we're going to end up just through this stable just situation of, hey, what's my best response to the other player? That's determined there. Through this scatter plot, we can then evaluate different indifference curve mappings, different levels of utility, and figure out from that which outcome may be socially preferred, may give us the highest levels of utility altogether, given our different preferences, given whether we are more selfish or given if we are more altruistic. Okay, that was the long form of that question because I'm explaining, going through definitions, all of the rest. Let's burn through a few more examples. We'll touch on all these points, but I don't have to go through the definitions and the explanation of each of them. We'll just do more of the walkthrough, talk through of, hey, what is the result? What is the different outcomes as we look at it? So I think I have 3 more altogether. Let's go take a look at each of those. Okay, in this scenario, we have choice of network provider. That is, in this case here, who's going to be providing our network for a car share network? Are we going to use Modo or are we going to use EVO? That is BCAA's program. Now, of course, to a degree, each municipality can choose which one they want to contract entirely on their own. However, there are network effects, there are network benefits if they link up, if they work together. Saanich residents get benefit if Victoria is also using EVO because now it's not just, oh no, I crossed a border, things are out of network. It's now all of a sudden, hey, it's the same network, things just work easier. Same thing with Modo. If they both choose the same one, they're both just, there's network effects compound. So what should we do? Given these payoffs, given the payoff to Saanich, given the payoff to Victoria, what is each of their best responses to what the other one chooses, presuming that either they need to make this decision simultaneously, or such that if they're not making it simultaneously, they're making it in isolation and you're not aware of the other's decision until after you've already made your decision. Okay, in that case, how do we do it? Same as we've always done it. We want to know what is our best response to the other player's choice. And again, just because it's my practice, I start with the row player, I start with Saanich. And all I would do is I'd say, okay, Saanich, what is your best response to Victoria choosing Modo? And if Victoria chooses Modo, we get either a payoff of 3, that's our benefit, or a payoff of 2. Well, 3 sounds like a better deal than 2, so we're going to go with 3. That is our best response to Victoria choosing Modo. What do we do if Victoria chooses EVO? Well, if Victoria chooses EVO, we can either get a payoff of 1 or a payoff of 4. So again, between these two, 4 sounds like the better payoff, and we see that Saanich would pick EVO if Victoria picks EVO. What I want you to see here is different from the other 2 games we looked at. Saanich does not have a dominant strategy. Saanich does not just always play Modo, does not just always play EVO. Their best response now does depend on what the other player chooses. So that whole dominant strategy, gone, not part of this. Dominant equilibrium, gone, not part of this game. To figure out where we may end up, we now need to switch our players and play as Victoria. Let's change our colors and do that. So now being blue, we can now play as Victoria, and we just want to do the same thing in reverse. We want to say, okay, if Saanich chooses to go with Modo, what is Victoria going to do? Well, could get a payoff of 4 or get a payoff of 3. Between the two, 4 is the better payoff. We get overlapping best responses. We have a Nash equilibrium at Modo, Modo. But don't stop just yet. Just because you found a Nash equilibrium doesn't mean you're done. What is Victoria's best response if Saanich chooses EVO? Well, if Saanich chooses EVO, we can either get a payoff of 0 or a payoff of 5. Well, hey, 5's better than 0, so we choose 5. And we have another set of overlapping best responses. Such that in this case here, we call this our coordination game. the best outcome altogether is the outcome where you can coordinate with your partner. Now, this is difficult if you cannot have that communication, either because communication lines have broken down or you're just unable to make this communication before you speak with each other. But what we see is that there are two ideal outcomes that we would want to end up at, such that we are just doing the same thing as the other. Again, keep in mind, Victoria does not have a dominant strategy. Victoria does not just always pick Moto. Victoria does not just always pick Evo. There is no dominant strategy in this case either. So no dominant strategies for either. No dominant strategies for either means no dominant equilibrium. However, there are altogether two Nash equilibriums, and that is at 3, 4, that is Moto, Moto, and at 4, 5, that is at Evo, Evo. Between the two, one of them would be socially preferred, but that is going to be just dependent on where they end up. That's going to just entirely be dependent on where they end up. So, how does this look in terms of our scatter plot? Well, let's go graph this and take a look. We have our vertical axes, we have our horizontal axes. Sanych is our horizontal player, so there we go. There's Sanych. Victoria is our vertical player, so there's Victoria. We have max payoff of 5, so let's set our scale maximum around 5 and 5. Doesn't have to be 5 for both of them, but why not? And then let's start throwing in our payoffs. Again, the big part, we're just eyeballing these. What do we have first? 3, 4. So that's 3 for Sanych, 4 for Victoria. I'm going to say that's somewhere around there. That is M, M. Okay, and let's just note for ourselves that is one of the Nash equilibriums. We then have our next point. Let's just go this way, 1, 3. So 1, 3, that's going to be something like that. That was Moto, Evo. And then go to the other extreme there, we have 2, 0. So if that's 1, if that's 3, 2 is going to be somewhere right in the middle, but that's 2, 0. That's down here. That was Evo, Moto. And then finally, the other Nash equilibrium, 4, 5. That's that to somewhere about here. That was Evo, Evo. And again, just to note, that was our other Nash equilibria. So, okay, in this case here, 4 possible payoffs, 2 Nash equilibria. How many Pareto efficient points do we have altogether? And again, what I want us to remember is that the definition of a Pareto efficient point is just such that there are no Pareto improvements possible. So that is such that we cannot be better off without making anybody worse off. So let's pick a point. Let's start with Evo, Evo. There is no improvements. There is nothing up to the right. No Pareto improvements from this point here. So that is, we are Pareto efficient. I'll do a check mark. We are Pareto efficient. What about Moto, Moto? Well, if we go up, if we go to the right, we see that Evo, Evo, Pareto dominates Moto, Moto. That is, both players are better off with that transition. So this is not Pareto efficient. We'll put an X there. We don't want that one from a Pareto efficiency viewpoint. It's not Pareto efficient. Even though they're both Nash equilibria, we're better off with that outcome than we are this outcome. Carrying on, Moto, Evo, straight up to the right. Again, we see we have 2 Pareto improvements that are possible to us. So again, this is not a Pareto efficient outcome because again, we could have a Pareto improvement. Finally, Evo, modo, we have two Pareto improvements possible from that. So again, this case here, we have Pareto improvements. This is not Pareto efficient. So in this scenario, we have a game, given our incentive structure, we have two Nash equilibria, two stable points that we could end up at. However, despite having two equilibria, only one of them is Pareto efficient. Out of all of our payoffs, we only have one Pareto efficient and Pareto efficient equilibrium. Just want to compare and contrast that for a second. Let's go jump back and take a look at our other case where we had biking, bus, or taking the car. So, okay, in this case, again, just to run through it, let's start up here. Nothing up to the right. That means, yes, we are Pareto efficient because there's no Pareto improvement. Nothing up to the right. So again, that means, yes, we are Pareto efficient because there's no Pareto improvement. Finally, nothing up to the right. So again, yes, we are Pareto efficient because there's nothing up to the right. In this scenario, we had three Pareto efficient payoffs because there were no Pareto improvement possible from any of these points. We did have one Pareto inefficient, and that was our Nash equilibrium. Our equilibrium was actually inefficient, and thus it was not Pareto efficient. We'll put an X there, and that's because there was a Pareto improvement possible. So just to compare and contrast, in this scenario here, our equilibrium was Pareto inefficient because Pareto improvements were possible. We had three Pareto efficient points, none of which being an equilibrium. Here, a little bit different. We only have one Pareto efficient point, only one Pareto efficient point, which happens to be an equilibrium, and such that the other three potential payoffs that we face, they all have Pareto improvements that are possible from them, meaning none of these other three are Pareto efficient. And so in this way, we can evaluate all the different Pareto efficiencies that take place. We could then throw on different indifference curves and go and say, hey, which one gives us the highest utility altogether, the highest payoff? Now, in this case, we're talking about conglomerations of people, Victoria of Saanich. It doesn't necessarily make sense to talk about utility in this sense because, like we said, you cannot amalgamate utility. You cannot aggregate utility from one person to the next. So there would not be utility functions that are attached to these because you cannot add up. Hey, what's the joy you get from a cookie plus the joy you get from a cookie? Makes no sense. So we can't necessarily add indifference curves in this context, given the players we are talking about. So that leaves us with that. Let's take a look at another scenario. Again, this other scenario, things we're looking for. Do we have dominant strategies? Do we have dominant equilibriums? What is the Nash equilibrium, if any? And then once we compare those Nash or dominant equilibriums, are they Pareto efficient? Are there Pareto improvements that are possible? Which points are Pareto efficient? Which points are Pareto inefficient? Let's go take a look at another example. Okay, often in this case here, people start to go, oh no, what's happening? Because now we have a bigger matrix. Turns out we can have matrices as big as we want. We could have so many options available to us. We often keep it 2 by 2 out of simplicity, and I will throw in a few 3 by 3s just to show the added complexity that comes with it. But although being added complexity, it's no more difficult to work through and figure out. And let's go walk through and see how we do this. Again, it's the exact same process. I will again start off with the row player, no reason other than just that is my practice. And the way that we'll do that is we then just fix the east player's strategies. And then we just say, what's our best response? So in this case here, we're looking at choices of energy grids. Hey, We could invest in solar, we could invest in wind, or we could just delay and maintain fossil fuel. Them, same kind of idea. Now, of course, best is going to be if we can align our grids because then they can feed off of each other and we have the same kind of current. Just for so many reasons, like similar with the last, the network effects win out. So I've probably given away this example as to the results, but let's work through it and see. So starting off, what is our best response if the east goes with solar? Payoff of 4, payoff of 2, payoff of 3. Which one's the best? 4 looks like the best payoff to me. So if they go solar, we go solar. What about if the east goes wind? Payoff of 1, 3, or 2? 3 looks like the best to me, so we go with 3. What if the east delays? Well, if the east delays, we get a payoff of 0, 1, or 2. 2 looks like the best there, so if the east delays, we delay. So again, in this case, the West does not have a dominant strategy. Their strategy depends entirely on what the East does, and their goal would be to match. Okay, what if we're now the East? Well, fix the West's strategy. Let's just change colors. So we're now the East, and what if we know for sure that the West is going solar? Well, we can get a payoff of 4, of 2, or of 3. Which one's best? 4 looks best to me. So there we go. That is our best response to solar. What is our best response to wind? 1, 3, or 2. There we go. We got our best response to wind is to also go wind. Finally, what's our best response to delay? We could get 0, 1, or 2. Again, 2 is our best response. And we see that we have 3 Nash equilibriums in this case. Again, the East does not have a dominant strategy. Their strategy is, again, do what the other guy's doing. And what we want is a coordination outcome where we're both doing solar, both doing wind, or both delaying. That is going to be our best payoffs altogether. These are our 3 Nash equilibria. To then go and say, well, okay, where is the Pareto efficient points? Are there Pareto improvements possible? Let's take a look at all of that. Where do we want to be? We can go and look at that by taking a look at the scatter plot. So let's go build that. So building these scatter plots, we have on the vertical, we're going to have the east. On the horizontal, we're going to have the west. So let's just go, oh, there we go, west, vertical, that is our east. And again, because these payoffs are always in terms of x, comma, y, so west, comma, east, row, comma, column. What do we have as max payoffs? Our max payoffs are 4, so let's go with that. Let's go right around there is 4. So about halfway down is 2, and then we can break it in half again, 1, 3. Similarly, we have 4, break it in half, about there, just eyeballing it is 2, and again, 1, 3. Great, let's start throwing in our different payoffs. So we have 4, comma 4, that is up here, solar, comma, solar. We then have 1, comma 2, right about there, 1, comma 2, that is solar, comma wind. We're going to have 0, comma 3, right about there, that is solar delay. Carrying on to the next row, we have 2, comma 1. With 2, comma 1, we have wind, solar, 3, comma 3. There we go, that's wind, comma wind. 1, comma 2. Oh, that's that guy. Again, we have that. This time it's wind, comma delay. It's okay, we can have the same payoffs, well, same payoff amounts for different ones. Next row, 3, comma 0, puts us down there. That's delay, comma solar. 2, comma 1, instead of wind, solar, that's delay and wind. And then finally 2, comma 2, 2, comma 2 is right there, and that is delay, delay. Okay, we now have all 9 of our points out, right? We can just count to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we've got them all. From here, we can then go through the whole process as to, well, which ones are Pareto efficient, which ones are Pareto improvements to other ones. That's how we define Pareto efficiency. And hey, let's just go and mark our Nash equilibriums. That was solar, solar, wind, wind, delay, delay. So those are our three Nash equilibriums that took place. So starting off with the one Nash equilibrium, solar, solar, going up to the north, going to the east. I guess that is kind of confusing because our players are east and west. So just going up, going to the right. We see that there is nothing up to the right of this. So yes, this point is a Nash equilibrium. This point is also Pareto efficient. Going and taking a look at the other ones, we have wind, wind, going up, going to the right. We see that both players could win by going from wind, wind to solar, solar. What that means is that this is not Pareto efficient because a Pareto improvement is possible. Going with delay, delay, again, going up, going to the right, we see that two Pareto improvements are possible. Again, if a Pareto improvement is possible, this is not Pareto efficient and thus suboptimal. Carrying on, what else do we have? There we go. Again, we have, that should actually be touching right at the same point, a little bit of error in scale. Let's just move it so that it does line up. There we go. Look at that, the magic of technology. We see that this is a Pareto improvement. The east is better off versus this outcome. The west is no worse off. So there is a Pareto improvement possible such that one is better off with no one being worse off. So this is not Pareto efficient because somebody can win without anybody losing. Wind, solar, again, in this case here, east is better off. And if we go to that one or that one, both are better off. So there's three Pareto improvements possible, meaning these 2 points are again not Pareto efficient. Carrying on, that should be just a little bit farther south. There we go, something like that, something like that. Again, we see from this point 1, 2, 3 Pareto improvements that could take place. Again, this is a Pareto improvement because the west wins and east is no worse off. So Pareto improvement. Because a Pareto improvement is possible, that means not Pareto efficient. Last case, 3, and going up like that. Look at that, I just missed it again on that one too. It's close enough though, I'm not going to adjust. We see again though, Pareto improvement. So there's 2 Pareto improvements from that point, meaning again, this is not Pareto efficient. So in this case, we only have one Pareto efficient outcome, solar, solar, and this solar, solar outcome also happens to be a Nash equilibrium. This is beneficial to us. That means if we can identify this by working through this in advance, and we hope the other player does the same thing, we can be fairly confident that we can choose solar and hope that our other competing player chooses the same, because we can recognize that we all win by making this choice. And so in this case here, solar, solar is not only one of our Nash equilibrium, it is also Pareto efficient. There are no Pareto improvement possible from that point. Let's go on to the last example that I have for game theory. Well, for this aspect of game theory at least. Okay, in the last example we have here, we have the payoff matrix of Linka and Kwame, who are both looking at, hey, do I put in low to high effort into my recycling efforts? Now, of course, if we put in high effort into our recycling, hey, we've separated everything. This just saves massive amounts of social resources. From society on whole, we're going to be better off if we individually put in that high effort. But that's somebody else winning who is so distant from me that I don't even register it. It's maybe somebody else has to pay to sort my trash. Oh well, that's them. I don't have to put in the effort. So we get this trade-off. Do I put in a lot of effort to self-sort, or do we just do no sort recycling, throw it all in a bin, and somebody else does it, potentially with a bunch of contamination, such that all that recycling just actually becomes garbage? Well, what do? Let's go play the game and see what the outcomes are. Let's start off with Linka. Again, just this is my default. So what we want to do is as Linka go, what is our best response to Kwame putting in low effort? Well, if Kwame puts in low effort, we can either get 4, 2, or 3 as our payoff. And between all of those, low effort seems to be the best. So if Kwame is putting in low effort, should also put in low effort. What about if Kwame does medium effort? Well, if Kwame does medium, I got 1, 3, or 2. Well, if Kwame does medium, my best response is medium. And then finally, what if Kwame goes high effort? I could do 0, 1, or 2. This is looking like our coordination game again, such that Linka's best outcome is to coordinate and do what Kwame is doing. Let's, of course, now flip the table and play as Kwame and see what Kwame ought to do. Okay, so we'll use green for Kwame. If Linka goes low effort, what is Kwame's best response? 4, 2, or 3? Well, best response there is 4. So we have a Nash equilibrium or overlap of best responses at low, low. If Linka goes medium effort, what is Kwame's best response? We have 3, 2, or 1. Kwame's best response to medium effort is low effort. And if Linka goes high effort, what should Kwame do? We got 2, we have 1, we have 1. We see that Kwame should again go low effort. What we see here is Kwame does have a dominant strategy. Kwame has a dominant strategy to always go low effort. So in this case here, we have one Nash equilibrium. We do not have a dominant equilibrium because we do not have overlapping dominant strategies. But we do have one Nash equilibrium, and we do have a dominant strategy from Kwame, which we know is low effort. If we were to go build our payoff scatter plot from this, we could do that. We would have Kwame on the vertical. We would have Linka on the horizontal. So there's Linka. There's Kwame. We've done labor and capital before. This is not labor and capital. This is Linka. This is Kwame. I'll say that again, and I'm sure I'll get questions about this. This is Linka. This is Kwame. LK. Okay, what are these payoffs? We have 9 of them all together. We have highest payoff again of 4, so let's put that in and then just eyeball it from there. If that's 4, roughly, that's 2, 3, and 1. Again, if that's 4, roughly halfway, that's 2. Split it again in half, 1 and 3. Okay, first payoff, low, low, that is 4. Low, comma, low. Next one, let's just go across the rows, 1, comma, 2. Something like that, that is low, comma, medium. We then have 0, comma, 3. 0, comma, 3, that is low, high. Then going to the next row, we have 2, 3, 2, 3. That is medium, medium. We have 3, comma, 2. Somewhere about there. 3, comma, 2, that is, my apologies, I got ahead of myself. 2, comma, 3. 2, comma, 3, that's medium, comma, low. 3, comma, 2. 3, comma, 2, right about there. That is our medium, medium. My apologies there, guys. Medium effort, high effort. So ML is 1, comma, 1. Medium, comma, high. High effort, 3, comma, 2. There we go. That is, we already have that point. That is high, comma, low. 3, comma, 2. 2, comma, 1. 2, comma, 1. That's going to be something like that. That is high, medium. And finally, 2, comma, 1. Again, well, that's the same as that one there. 2, comma 1, yet again, that's high, comma high as well. Okay, we should have 9 points altogether because it's a 3 by 3 matrix. Let's just confirm. We have 1, 2, 3, 4, 5, 6, 7, 8, and 9. There we go. We've got them all. Let's go through. Let's identify any Pareto improvements and what the Pareto efficient point or points are. So again, starting with low, low, that's at 4, comma 4. We have nothing up to the right of that. No Pareto improvements, so that is Pareto efficient. The next one we can take a look at, this guy here. We see, oh, we could have a Pareto improvement, so nope, that guy is not. This one, yes, we have another Pareto improvement, so that's not Pareto efficient. And as I carry on, I see the same kind of thing happening everywhere. Every other point that I take a look at is a Pareto, or rather has a Pareto improvement that is possible from it. So in this case here, we have the 1 Nash equilibrium. Oh, let's use the right tool there. We have the 1 Nash equilibrium, which is also the 1 Pareto efficient point. And so there we have a case that, hey, both aligns. Both the Nash equilibrium being solo and stable, and also being, in this case here, that joint payoff being the highest, being the Pareto efficient point. So a few different things we've done in this video. We have ultimately seen how to play our simultaneous games. We have had a payoff matrix, as we've seen here. We've seen 2 by 2, we've seen 3 by 3. We've gone through to identify each player's best response given what the other one is going to choose. We found then dominant strategies. Dominant strategies are like in the case of Kwame here, such that Kwame always does the same thing, irrespective of what Linka does. We'd say Kwame has a dominant strategy. We also have dominant equilibriums, which is where we had overlapping dominant strategies. Linka does not have a dominant strategy, so there is no dominant equilibrium in this case. We had our Nash equilibrium, which was our overlapping best responses. We see those overlapping best responses right there, where Linka's best response to Kwame's actions and Kwame's best response to Linka's actions overlap, giving us our stable equilibrium. From these payoff matrices, we then went to our payoff scatter plots, and we use these payoff scatter plots as a way to identify Pareto efficient points, Pareto improvements, and potential Pareto improvements, as well as Pareto dominating points. Again, Pareto domination, low, low, Pareto dominates in this case, just having a quick look at it, looks like low, low dominate, Pareto dominates everything. And again, it Pareto dominates everything because it's a Pareto improvement to every other point. We could say that ML Pareto dominates LM, however, LH does not Pareto dominate LM because that is not a Pareto improvement. So again, Pareto domination, if you are Pareto dominated, it just means that a Pareto improvement was possible. So taking a look at a bunch of aspects of the Pareto criterion using these scatter plots. We did also look at the difference between selfish and altruistic indifference curves and how that can impact in which outcome, which payoff would ultimately be preferred based off of different levels of indifference or different preferences, rather, between being entirely selfish or being altruistic. That doesn't necessarily change the way we play the game. It just changes which final outcome may be most preferred by each individual. If you have any questions on anything we went through in this video, of course, feel free to leave a comment below or send me an email. Until next time.